Okay, so here in this video, we're going to work on finding the area between two curves. So suppose we have a function f right here, and it's bounded by the x-axis, which you know is y equals 0. So that, say, is our second curve. And we're going to go from x equals a to x equals b. So the area that we're talking about is right here. Well, we already know that the area of that rectangle is delta x times the height. Well, the height of that rectangle here is very easily f of x. You take an x, you put it into the function, and that would tell you how high the rectangle is. So we know that the area of one rectangle here is f of x times delta x. And we want the summation of all those areas, so that will entail taking the definite integral from a to b of f of x times delta x. So this is how we're going to find the area between two curves. We'll take the height of the rectangle, multiply it by its width, which is delta x. This height of the rectangle is what's going to change quite a bit. So if we have a different picture of a function f, and this time the second function is not the x-axis. Suppose it's a function g. So we're going to be bounded once again from x equals a to x equals b. This is the enclosed region we're finding. So we'll draw one rectangle. Always draw a rectangle to indicate the area that we're finding. So the area of that one rectangle, of course, again is delta x, the width of the subinterval. But this time, the height of that rectangle is not easily f of x, because I have a function g. So let's think about that. How high would that rectangle be? Well, if we were up here at, 5 and, we have a point down here at 3, well, how long is this segment? You would say 5 minus 3, which is 2. Well, how long would each of these rectangles be in this interval from a to b? Well, it would be simply the top function, f, minus the bottom function, g. That would tell us how high the rectangle is. So here, even though we don't have functions yet, we're just talking about how to set up to find the area between these two curves. We write it as the area from the definite integral from a to b of f minus g dx. Here's the important thing to remember. When we are drawing our rectangle vertically, the width is delta x right here. The height of the rectangle will be the top function minus the bottom function. Top minus bottom. That's the key. That's the height of each rectangle in that interval from a to b. Now we'll often have pictures where f and g intersect each other. And perhaps we want the area between those curves where f and g intersect each other. They don't always have to intersect. Like in this case right here, they did not intersect. But perhaps in this case where they do intersect, it just means that the limits of integration will be where the two functions intersect each other. So once again, we draw a rectangle to indicate the area between the two curves. So that area here in this case would be equal to, I kind of didn't label it very clearly which function is which, because I have both f and g here at the intersection. So let's label the top function f and the bottom one here g. So once again, it would be the definite integral from a to b of the top function right here minus the bottom function g dx. And what you'll do is you'll just put these functions in terms of x, run the negative sign through carefully, take the antiderivative, and evaluate that at the limits a and b. Now what about if we have a case where we don't have functions of x, but we have functions of y? This will result in like a y squared equals x. That is not a parabola concave up or concave down. It's a parabola, as you may recall from last year, spun sideways, like that. So y squareds, remember, their shape go sideways. That would be a positive y squared, and a negative y squared would go like that. They are functions of y, not of x, because they fail the vertical line test. And suppose we have a function, another function of y, that's being spun this way. So let's call this function g and this function h. Here, it would be too hard to find the area by drawing the rectangle vertically, as we'll discuss in future videos and future lessons. It would be best to draw the rectangle sideways, right here, sideways. So here's the bottom line. When your graphs, if you will, are going sideways, in which they are functions of y and not of x, meaning I can easily solve it for x equals y squared, it's a function of y, not of x. Draw the rectangle sideways. So what's the area of that rectangle? Well, the area of that rectangle right here, this right here, the height now is your difference in your y's. That's your delta y. Now this right here, the width of the rectangle, well, how long is this? Well, let's just think. If we were out here at the x-axis at 10 and somebody else was back here at 5, the distance between those 2 points would be 5. 10 minus 5. We did right minus left. Over here, we did top minus bottom. And the reason being is distance can never be negative, and neither can area. So that's why we always do the top minus the bottom, because the function that's on top is the bigger function. Over here, when we're doing right minus left, the function on the right will be, if you will, the bigger minus the smaller. So here, this would be the definite integral, and we'll call this intersection from C to D. Now these will also be y. That's what's going to change here, is that if this is in terms of y, then these limits of integration have to be in terms of y. I'm going to go from this y, which is maybe say -2, to this y, which is 3. So back to the width of this rectangle. The width of the rectangle will be the right minus the left. Again, how long was this segment right here from 5 to 10? It was 5. I did right minus left. So here, this would be g minus h. And this, of course, will become our dy. So the actual width of this rectangle is the g minus y. But what these will become inside here is they will be in terms of y's. They are functions of x, which means, think about it, that we're talking about horizontal distance. We're talking about the difference in the x's. These x's will be functions of y's. So if this is a y, and these limits are a y, these need to be in terms of y then. So it would be right minus left. Back over here, when we drew the rectangle vertically, it was, this of course is our delta x, that was our width, and our height was top minus bottom. These are functions of x's, and that's why we ended up with the integrand all in terms of x, because they were functions of x's. And the height there is the difference in the y's, but the y's are functions of x's. It was a top minus the bottom. It was this y minus this y. Over here, it's going to be in terms of y's because of the fact it's the difference in the x's which are really functions of y's. So the bottom line is, when you draw your rectangle horizontally in the integrand, this will be always y. It will be a right function minus the left function dy. And over here, when we draw them vertically, it will always be the top minus the bottom.